So let's start section 1.9, the matrix of a linear transformation. We've already introduced the idea of linear transformation and the matrix of a linear transformation in 1.8. We're going to take those ideas a little further here in 1.9. A matrix that has the same number of rows and of columns is called a square matrix. Sometimes we just say an n by n matrix, right? We imply the number of rows and columns is the same by using the same letter for the number of rows, number of columns, n by n. And here's I'm just going to draw a picture of this. And so here's a 3 by 3 square matrix. What I circled is called the main diagonal of a square matrix. I think that says enough. And n by n square matrix that has ones as entries on the main diagonal and zeros elsewhere is called an identity matrix and is denoted IN. So here are some examples. I2 looks like this. Ones on the main diagonal, zeros elsewhere. I3, the 3 by 3 identity matrix, has ones on the main diagonal, zeros elsewhere. I4 looks like this. And so you can see the pattern. So why is this matrix special? Let's just take a look at an example of the 3 by 3 identity matrix, I3. And I'm going to multiply it by any old vector ABC, so any three-dimensional vector. And so here it is, the I3 times ABC. And what do? We take A times the first column plus B times the second column plus C times the third column. And what do we get but ABC? So for any vector V and Rn, if we take In times V, we get V. So this matrix that has ones in some positions, zeros in others, is special because it works kind of like the number one when you multiply, because if you multiply times a vector, you get that same vector back. The columns of I sub n are traditionally denoted as vectors, but with the letter E. So E1, E2 to En. So we would say I2 has columns E1 and E2. I3 has columns E1, E2, E3. Now notice E1, we use the same notation, E1, for different dimensions. So you have to know which dimension you're in if you just write down E1, am I in dimension 2, dimension 3, dimension 4, 5, 6? That depends. So that the meaning changes depending on the dimension that you're in. And that will be clear. That's never meant to be a mystery for us. Now let's look at an example. So we're going to let T from R2 to R3 be a linear transformation such that for E1 and E2 in R2, so that's the domain space, T of E1, which is just T of the 1, 0 vector, is equal to 2, 1, 0. So I made this up. This is an example I'm just making up. And T of E2, which is T of 0, 1, is going to turn out to be negative 1, 3, 5. So what we're going to explore is, if you know what the image of E1 and E2 is for this linear transformation, we really can find the image of any vector because of that. So here's why. Let x be any vector in R2 with components x1 and x2. We're saying, what is T of x? What is the image of x under this transformation? So notice we can write that vector x, x1, x2, as x1, 0 plus 0, x2, right? And now I can factor out a scalar, x1 from the first, x1 times 1, 0 plus x2 times 0, 1. And we can write it in this way. The scalar x1 times the vector e1 plus the scalar x2 times the vector e2. Now, by properties of linear transformations, T of x, which is T of x1 e1 plus x2 e2, we can, this was at the end of the previous section, we know, because this is a linear transformation, that that image must be x1 times the image of e1 plus x2 times the image of E2. And we know what the image of E1 and E2 are for this linear transformation. That was given right up at the beginning. Those, in fact, that was the only information we had about the linear transformation. So we fill that in, we multiply by the scalars, and we add the vectors back together. And what we have here is the image of x. So here's the rule for how to get the image for any vector x. And it all hinged on what the image was for E1 and E2. And in fact, we can write this column vector as a matrix times a vector, because the first column would be the coefficients of x1, 2, 1, 0, 2, 1, 0. Second column would be the coefficients of x2, negative 1, 3, 5. And you can just check, multiply this out, it'll take you right back up there. So notice, though, what's interesting is these columns of the matrix that defines this linear transformation are just the image vectors for E1 and E2. In fact, I could have got that matrix just by using these two column vectors as the columns for the matrix. And of course, we're going to do that from now on. We want to be able to take advantage of this shortcut. So in our notation, we're saying this linear transformation is AX, where A is a matrix with these two columns, T of E1, T of E2. And we're going to make a general statement of that. Now the general statement's kind of abstract because we're trying to deal with any dimension here. So theorem 10 in our textbook, let T be a transformation from Rn to Rm, a linear transformation. Let A be the m by n matrix whose jth column is T of Ej, where Ej is the jth column of In, the identity matrix in Rn. So A is a matrix with these columns. Then T of x is A times x, meaning A is the matrix that defines this linear transformation. The matrix A is unique. There's only one way to do it. And A is called the standard matrix of the linear transformation. Let's go ahead and do an exercise here. So we want to find the standard matrix for a particular linear transformation. This is from R2 to R2. And now I'm not giving you specific image vectors here. I'm just drawing a picture. And I'm saying this is what the linear transformation T does. It reflects a vector through the y-axis in the xy plane. Now, notice this picture here. When we have a transformation where the domain and codomain have the same dimension, so they're both R2, we often draw both the input vectors and the image vectors in the same coordinate plane. So here's a u, an input vector. Here's its T of u, the image of u. Here's v. Here's the image of v. And I'm just looking at the most technically drawn picture in the world, but I'm trying to just show this idea of reflecting through the y-axis. That's what we're doing, right? Now, if we want to find the standard matrix for this transformation, what we want to do is we want to find T of E1 and T of E2, where E1 is just the 1, 0 vector, and E2 is the 0, 1 vector. So those are the two columns of the 2 by 2 identity matrix, right? And so I'm going to go into the xy plane, and I'm going to imagine both of these vectors. Now E1 either can be thought of as the 0.10, right, which is like 1 unit out on the x-axis, or we can draw an arrow emanating from the origin. Here's E1. And the image of E1 under this transformation, if we reflect through the y-axis, is going to be like that, right? So I can just visualize this. And I know this is going to be the point with coordinates, x coordinate -1, y 0. So it's not too hard to see here that t of E1 is going to be -1, 0. Now E2 is going to point up along the y-axis, 1 unit up. Right? So the coordinates of this point are 0, 1. And when I reflect that through the y-axis, it doesn't go anywhere. It just stays put, right? So E2 is equal to t of E2. So t of E2 is still just 0, 1. Okay. So the standard matrix for t is just going to have columns t of E1, t of E2. You don't have to write all this down each time. I'm just going to use these two columns, -1, 0, 0, 1. So there's our answer. We were just trying to find that. And it turns out to be a fairly simple matrix. And we're done with that. And I just want to check what it does to any vector with coordinates x1, x2. So say we take any vector that comes out to this point, x1, x2. Notice that if we multiply -1, 0, 0, 1 times x1, x2, what are we going to get? I'm going to get x1, -1, 0, plus x2, 0, 1. I'm going to get -x1, x2. So the image of this x1, x2 vector will be a vector with opposite x-coordinate, same y-coordinate. That would just point out over here in this picture. This would be the point -x1, x2. So we didn't have to do that. The answer is up here, but that just confirms that this matrix multiplication will reflect any vector through the y-axis. And so we'll pause and continue in another segment.